All right. Good morning to those of you who are, the 6 of you who are logged in, well, 5 of you. We'll wait a couple of minutes and then we'll get started. And while we're waiting, if you have any questions, feel free to ask. All right. Let me put a page in here. All right. So today we're going to start talking about the concept of conjugation. And with that idea, we're also going to talk about like, we're going to give the definition, obviously. Hopefully you had a chance to watch the videos that I sent out or read the section in the book or both. So we'll talk about the definition. We'll talk about why it's special. We'll talk about a little bit of molecular orbital theory. And yeah, and then the reactions of conjugated dienes. All right, so we want to talk about addition of HX to conjugated dienes, and we're also going to talk about Diels-Alder cycle addition. All right, both of those are two totally different reactions, but they both use conjugated dienes as the reactant. All right, so can somebody give me a layman's definition of conjugation based on what you read or what you viewed?
A pattern of alternating double bonds and single bonds. But
Okay,
it could also,
go ahead.
oh, I was just saying it could also be triple bonds.
Sure, excellent. So it's the by definition, it is a system of alternating double and single bonds, or sigma and pi bonds. That's how I like to say it, because it doesn't have to be a double bond. Right, so as a simple example of a conjugated system, we always look at 1,3-butadiene. Right, and the reason why this is even possible is because there's a p orbital on each one of these carbons, right? And so that sigma bond in the middle gets compressed, right? The bond length shortens because those two sp2 carbons are pulling on one another's nuclei. So as they do that, they shorten that bond and they allow these 4 p orbitals to kind of exist as, excuse me, as a unit. So that sp2 attraction of these two sp2 carbons, it kind of creates, because of the electronegativity of those carbons, it kind of creates a little bit of compression with that sigma bond, right? So that system is considered conjugated, and that's why it's important for the pattern of alternating sigma and pi bonds to be present. Otherwise, you can't have that compression. You don't have that overlap between those two p orbitals right here. And then, so the system wouldn't be considered conjugated. All right, so we look on the, and I think I downloaded this. Hold on one second. Let me look in the downloads folder, because I can put this in the chat for those of you who don't have it yet. I think I downloaded it. Please, yes, I did. So let me put this in the chat real quick. I'll upload it for you to grab. So I'll put the handout that we're working from today, or we'll be working from this week and next week. I'll put that in the chat so you can grab that to make it easier for you to follow along. All right, so this is an example of a conjugated system, right? There's a pattern, and that's how you recognize it. You look for that pattern of alternating sigma and pi bonds, or pi and sigma bonds. So you can see there, you have a pi bond, you have a sigma bond, and then you have another pi bond on the other side of it, right? Over here, same thing. You can have triple bonds that are conjugated with one another. So you have pi, sigma, pi. That's the pattern you're looking for. All right. If there's more than one bond between the two pi systems, then there's no conjugation, because these two orbitals, the p orbitals right here, can't talk to each other. So there's a p orbital here, there's a p here, but the distance between them is too far. Right. So the distance between them is too far, so those two p orbitals can't talk, and so that system is not conjugated. Each one of these pi systems is separate. So it's not conjugated. All right, so let's take a look at some molecules down here, and we'll just walk through them and determine which ones are conjugated, which ones are not. And yeah, so let's work through some of these examples. So let's look at that first example. What do you think here? Do you see the pattern of alternating pi and sigma bonds?
Yes.
Yeah, you can see it, right? There's a pi bond here. Let me make this a little thinner. We got a pi bond here, and then you have a sigma bond here, and then adjacent to that, you got another pi bond. This is an example of something that what we call fully conjugated. Right, you can have conjugation, but it's not fully conjugated. It can be partially conjugated, but this benzene is an example of something that is fully conjugated. And what that means basically is that there's a p orbital on every carbon. So if I were to draw out this benzene like so, every one of those carbons in that ring will have a p orbital on it. Right, so when something is fully conjugated, that means that there's a, and this is important, an important idea for the next section, which is I think aromatics that we're going to be talking about. Right, so there's a p orbital on every carbon in that molecule. So that makes it fully conjugated. All right, any questions about that example? All right, let's look at the next example. What do you think? Is that conjugated or not?
No.
Can you see the pattern here? It's not fully conjugated, but it
Oh,
is.
I see.
You see the double, single, double, or pi, sigma, pi? So you have two pi bonds separated by a sigma bond, so yes. Right? Ooh, I don't know who that was that said no, but do you see it now?
Yes, I do.
Okay, all right, cool. Right, same with this one. You can see the pattern. These are my pi bonds, and each pi bond is separated by a sigma bond. Right? All right, so is this one fully conjugated, do you think? Can we put a p orbital on every carbon in here?
No.
Is that okay? Everywhere there's a pi bond, the two carbons involved in that pi bond both have p orbitals because the pi bond is made up of two unhybridized p orbitals overlapping with one another, right? So this is also fully conjugated, and it fits into the same class as benzene, which is what we call an aromatic compound. Right, there's a definition for, and we're going to talk about aromatics, but I can go ahead and introduce you to the definition now. So it's planar, cyclic, it's fully conjugated, and it meets the 4n+2 rule or the Huckel rule. All right, that's the definition of an aromatic compound. So benzene, and this is naphthalene. Both of those are what we consider aromatic, right? It's fully conjugated, and let me put here, I was going to put aromatic here. Right, so aromatic compound is a it's a conjugated compound. Also, it's not a conjugated diene, but it's a conjugated compound that displays conjugation as one of its major properties, right? Full conjugation. All right, what about here?
Yes.
Yes.
So where's my other pi bond? Because in order for it to be conjugated, I need at least two pi
At least
bonds.
two.
Yes.
Okay.
So a diene is so it's got to be at least a diene, right? we have two pi bonds. So if you have one pi bond, it can't be conjugated, right? Because the conjugation is not just the pi bond itself, but it's the pi bond being able to overlap with a second pi bond, right? So if I had another pi bond drawn in here, then yes. But the fact that it's just a single pi bond, it cannot be conjugated. It has to be, at minimum, it has to be a diene in order to display conjugation. Right. And then if it's a diene, it has to follow that pattern of pi, sigma, pi alternating. What about the next one? Right here. What
No,
do you think?
not conjugated.
No, it's not. You have a pi, but then in between that pi and the other pi, you actually have two sigma bonds, right? Do y'all see that? You have a sigma here and a sigma here. In order for it to be conjugated, you need that pi bond to be separated from the second pi bond by one sigma bond, not two. All right, what about the last one?
Would this one be
Yes.
yes, since
Yeah.
there's only one sigma bond in between?
Yes, you see the pattern, right? You got, excuse me, pi, and then sigma between them. So yes. All right. Now it's not fully conjugated, obviously, because there's not a p orbital on every carbon in that molecule, but it is conjugated, right? And this is an example, just like we looked at up top, of what we call this is a conjugated diene, right? Di meaning two, ene meaning alkene, so it's a diene, right? Same thing here. This is also a diene, but it's not conjugated. It's a non-conjugated diene, right? This also is a conjugated diene. So that's where we are, like the umbrella that we're going to be working under is conjugated dienes, right? And how they react. Right. So let's talk. I said I was going to introduce a little bit of molecular orbital theory. So let's talk about that on the next page here. Right. So you see where it says conjugation occurs when the p orbitals from which pi bonds are formed overlap with one another. So you can see that right here. Right. The p orbitals are here, 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 and here. And again, the overlap is made possible because of compression of this carbon-carbon sigma bond. Right, and that what happens in this case is rather than having just two separate pi bonds, that overlap makes this system go from just two separate pi bonds to what we call a 4 pi system. Right, that's what we call a 4 pi system, because you have two pi bonds that are conjugated to one another, and then there are 4 pi electrons. 4 pi electrons. So y'all following that? Because each one of these p orbitals has one electron in it. Ooh, that's ugly. All right. Questions about that? All right. So what that means for this 4 pi system is it's going to behave a little bit differently, right? So you have 4 p orbitals. And what that means in terms of molecular orbitals, which is another way to think about how these systems react, you'll get 4 molecular orbitals. Right? And so I'm gonna cut this out and so I can, wrong pen. I'm gonna cut it out. And I'm gonna show you the molecular orbitals real quick. Right, so when we talk about molecular orbital theory, the way that molecular orbital theory describes conjugated systems like this is you basically give electrons properties of a particle and a wave. So you basically use a standing wave theory to describe it. So let me show you that. So with a wave, right? With a wave, this is the first harmonic. How many of y'all have had physics and have already studied waves?
I have.
Okay. So this is the first harmonic and the wave never passes through 0, right? If you go up to the so this is the energy level here is 0, right? It's the ground state. It's the lowest energy level possible. You go up to the next energy level, and then you have what's called the second harmonic, where the wave passes through 0 one time. Right, and then you go to the next energy level, right? The wave is going to pass through 0 twice. Let me fix those nodes. All right, so this is a third harmonic. I'm only going to go up to 4 because that's what we're going to apply to our 4-part system. All right, and then in the fourth harmonic, the wave is going to pass through 0 3 times. So 1, 2. Hold up. Like so. So this is the fourth harmonic. So the way that this applies to like pi systems, well, let me fix that. The way that this applies to pi systems is if you assign the characteristics of a wave to your pi system, then every pi system is going to follow this pattern, right? What it's really saying is that those 4 p orbitals have 4 different ways that they can combine to make what we call a molecular orbital. And then you use the molecular orbital to describe how that 4-pi system behaves when it reacts with other things, right? So basically, so I got these 4 p orbitals working in concert because, again, the conjugation makes them work together as a group. So I got these 4 p orbitals that can combine in 4 different ways. And as you can imagine, this can be extrapolated to larger conjugated systems like 6p systems, 5p, 7p. Like you can have as many p orbitals as possible if it's conjugated. All right. So these molecular orbitals are going to have wave-like properties, right? So in that first harmonic, and before we do this, how many of you remember from organic 1, if you have a p orbital, right? It has 2 lobes, is that right? And then one of those lobes has a sign and the other one has the opposite sign. Do y'all remember that from part 1? Because in between them, there's what we call a node, a place where the wave passes through 0. All right. So the shading is just a sign, right? Because it's an equation. And so it can be the positive or negative. So the shading part is just a sign of the equation. So if the wave never passes through 0, then the sign of the p orbital equations is never going to change in that first harmonic. All right. Yes, no, maybe.
Yes.
All right. What about when the wave passes through 0 one time in the second harmonic? What do you think? The sign should change once. We're going to talk more about this. I'm just introducing it now. All right, and then up here in the third harmonic, when the wave passes through twice, and it's got to be symmetrical. I'm not going to pass it through on an orbital if I don't have to, although there are some cases where that's possible. All right, so this is going to be here, like that, and here, right? Because again, those p orbitals have a specific sign, and they're going to follow the pattern of the wave. So whenever the wave changes signs, so will the orbitals. And up here, this passes through 3 times, like that. So you have 3 places where the wave changes signs. So these are just going to be alternating like so. All right. So that's what your 4 molecular orbitals look like for a 4-pi system. And all of this is possible because of conjugation. Right, that 4-pi system is for conjugated diene. Those 4 p orbitals act as a unit. They work in concert with one another because of that overlap between those 2 middle orbitals. Right, so if you have a 6-pi system, then you're going to have 6 molecular orbitals. And each molecular orbital is going to contain 6 p orbitals, because that system, those orbitals can combine in 6 different ways. All right. If you have a 10-pi system, it's going to have 10 p orbitals and then 10 molecular orbitals, so on and so forth. So you'll see that. We'll talk more about this when we talk about cycloaddition. Deals all the cycloaddition, because there's another aspect of this that I'm not going to touch right now. I just wanted to introduce it. So let's go back to here. And it says here, draw the p orbitals for the following system and tell why it's not conjugated. So why is this system not conjugated?
Because of the sigma bonds in between the gap between the pi bonds.
Yes. So right here, right, there's 2 sigma bonds here instead of 1. So what does that mean for if we were to look at the molecular orbitals for this? Would those two pi bonds be independent, or would it be 4 pi, a 4 pi system? There's no bad answer, because if it's wrong, it could be corrected. And if it's right, that means you caught what we were just talking about. But either way, it's good. So what do
Can
you
you
think?
ask the question again?
I was asking if those pi bonds are going to act independently, or will they act like a unit, like a 4 pi unit?
Independent.
Yes, because they're not conjugated, right? So the fact that these two pi bonds are not conjugated, they're going to act independently of one another. All right. And that's the consequence of conjugation. If they were conjugated, then they act as a unit, but because they're not, then they don't. All right. So now we're going to jump in and look at one of the applications of conjugated dienes, which is the addition of HX to conjugated dienes. All right, HX being some acid like HCl, HBr, HI, something like that. So look at that first reaction. What is DBN? Anybody remember? I'll put lunch on the table if you could tell me what DBN is. I need some Jeopardy music.
It's like dimethylflomidide.
You try to get that lunch though. But no, think back to what the section we just studied. Right? Think back to the section we just studied. We looked at substitutions and eliminations, and DBN was one of the things that we actually studied as a part of when we were studying eliminations. All right. So DBN.
Is it C7H12N2?
Say that again.
C7H12N2.
All right. So it's a base. Let me pull it up so y'all can see.
Amidine.
Let me pull it up. It was in that elimination video. It's right here. You're right. You call it the amidine base. Did you just Google it? Who was that, by the way? Because we only had like 2 guys in the class.
AG.
All right, I got you.
Now I had it in my notes.
Okay, all right. Put your Cash App in the chat. You got close, so I'll take it. So it's right here, right? And so it's a strong base. It's a base that's used for elimination. All right, so let's go back to here. So if I have a strong base, and then I have a good leaving group, and tertiary substrate, what's going to happen here? We did talk about that leaving group, that triflate leaving group.
A E2 reaction.
Come on with it. Come on with the come on. E2 elimination. Where's the elimination going to take place? Where's my alpha proton? Right? You have two sites, but this is not acidic because it's a vinyl proton. It takes a lot to pull that off. So it's not acidic. Where's my other site?
Above the OTF.
Right here.
Yes.
So those are your two alpha sites, but the fact that this is a vinyl protons, you see how it's attached to a double bond? We call that a vanillic. The pKa of that proton is like 46 or 47. Very difficult to pull off. Right, but the one above it, we can do that. So what is my elimination product going to look like? And then DMF is a aprotic solvent, right? So that just goes right along with the E2 elimination thing. So what's the product going to look like?
It's gonna be a double bond.
So this one is already here. I'm gonna put it right there. Y'all following that? The base is just gonna come in, pull this proton off, and eliminate like so, like that. So it'll be that plus OTF plus H. I'm just writing this as HDBN. All right, anybody not see that? All right, that's a standard E2 elimination. All right, what about in the next question? It says, is the product a conjugated diene?
Yes.
It is. Yeah. All right, so here's my product, and it says use the product from the reaction above and consider the following and propose a mechanism for the formation of the products. All right, so before we jump into that, I'm gonna give you a generic example first. So let me take that. I'm just gonna paste this. All right, so let me give you a generic example, and then we'll go back and look at this example. All right, so if I took just a standard conjugated diene, plus HBr, what's going to happen with that? Somebody who watched that, the first conjugated dienes video, tell me, what do I get from this? And how does it happen, right? Remember from part one, anytime you have an alkene in the presence of an acid like HBr, HCl, HI, first thing that happens is you do proton transfer. So the alkene is acting as a, in this case, as a base, but it can also act as a nucleophile, right? So with these conjugated dienes, you get this intermediate that's common right here. So there you have Br, kind of sitting out here waiting to pounce on this. But this is what we call an allylic cation, right? That intermediate is important because now the allylic cation can actually get attacked two different ways. So here is one way, and then here, the fact that I can do resonance means I can do this too, and I put the plus charge here. Following that? Anybody not see that?
I see that, but is there a reason that you chose that alkene instead of the other one?
No, it's symmetrical because that's a symmetrical alkene, so it wouldn't matter which side you chose. And to be honest, if it's a conjugated diene, you're probably going to get, if it's not symmetrical, you're probably going to get four products, right? Because this one alkene reactant is going to give me access to two products, right? Because bromine can attack here directly. We call that 1, 2. Or it can attack here. Like so, we call that 1, 4 attack. You can also call it resonance attack. All right, so that's going to actually give me two products. One with the bromine here, and I gotta shrink that down just a tad. And then the other product with the bromine here. Like that. So this is my 1, 2, and this is my 1, 4 product. Right, so anytime you have a conjugated diene and you add HX to it, it's going to go through this mechanism where bromine can attack directly at the plus charge, or it can attack the resonance form of that cation. All right, and these products are temperature dependent. I know that for a fact that's in that video. So we're gonna hit that other example hard when we come back because we only got 4 minutes left. So when we look at any questions about this first before we look back at that example? So it's asking, says use the product from the reaction above, consider the following proposed mechanism for the formation of products. So here, this is unsymmetrical, right? You got an alkene here, you got another one here. And so you're actually gonna use both. But when we come back on Wednesday, we're gonna look at that and we'll be able to walk through the mechanism and talk about the temperature dependence and all that stuff. All right, any questions about anything? Let me grab this chat too before I close the meeting out. All right, no questions. Everybody good? Did y'all go to Mobile this weekend? Let me turn the recording off. I don't want to incriminate nobody.